Alright, hello everyone. I hope you guys are doing great. So today I'm going to be discussing the solutions to this Google Kickstart round C. And talking about the round, I think it was a pretty balanced Kickstart round. And the first two problems were really easy. And the last two problems required some keen observations, especially problem C. But I would still say that the last problem was typically easier than general Kickstart problem Ds. But anyways, it was still good enough, I think. So yeah, overall a pretty balanced round, I would say, right? So today I'll be discussing the solutions to all the problems. So without any further ado, let's start with the solution to the first problem. So a company named Google has issued a new policy that their employees' account password must contain. So there are these 5 conditions that the string has to fulfill. First is that it should has at least 7 characters, then it should have an uppercase letter, it should have a lowercase letter, then it should also have a digit, and it should have a special character which is one among these 4 characters. Okay. And now we have been provided with the password, and we need to tell what is and we need to append the minimum number of characters to this password such that all these 5 conditions are satisfied, and we need to output a valid password which has minimum length and all these 5 conditions are satisfied. So the solution here is pretty simple. What we can do is we can simply check for all the 4 conditions from 2 to 5 whether there is an uppercase letter, a lowercase letter, a digit, or a special character. So and then if these conditions are not fulfilled, then we just add an uppercase letter. If there is no lowercase letter, we just add a lowercase letter, similarly for a digit and similarly for a special character. And once we are done with all of that, we check if the length of the string is at least 7 or not. If it's not, then we keep adding some arbitrary character until and unless the length becomes 7, right? And that will give us the valid solution. Okay, so let's just have a look at the code. The code is pretty simple. What we do is we keep these boolean variables which denote whether there is an uppercase, a lowercase letter, or a digit, or a special character. Initially all of them are false, and as and when we find these characters, we just say that the value of these boolean variables are true, and then we check if there is no uppercase letter, we add an uppercase letter, same for a lowercase letter, same for a digit, and same for a special character. And then until and unless the length of the string is less than 7, is greater than or equals to 7, we keep adding an arbitrary character. In my case this is 1. You can add any character of your choice, right? And that will be a valid solution, and it will definitely be a string of minimum length. Okay, so yeah, pretty intuitive, not much to talk about in this problem. Okay, so yeah, this is the first problem. Let's now talk about problem B. Range partition. Again, this is a pretty simple problem. So let's see what this is saying. So Alan and Barbara felt like playing a game with numbers. So Alan chose a non-empty subset from the set of first n positive integers, and Barbara takes the rest of the numbers from the set. Okay, so basically there is a set which contains the first n natural numbers, and Alan is taking an arbitrary subset from this set, and all the remaining numbers are going to Barbara. Okay. Now the thing is that Alan wants to choose his subset in such a way that the ratio between the sum of numbers that he chooses and the sum of numbers that go to Barbara is exactly equal to x over y. Okay, here x and y are numbers whose GCD is equal to 1, obviously. So we have to help Alan choose its subset, right? So what we have to do is we have to tell exactly which numbers should Alan choose such that the ratio of the sums of numbers that Alan and Barbara have is exactly equal to x is to y, right? So let's talk about some very simple to make observations here. So one observation is that the total sum is conserved. So total sum is conserved. So total sum of numbers of Alan and Barbara is going to be nothing but the sum of the first n natural numbers, which we all know is equal to n into n plus 1 upon 2. Okay, so this is a very basic formula for the sum of the first n natural numbers. So yeah, this is the total sum of all the numbers that Alan and Barbara will have. So let's say that so now we know that for Alan and Barbara to have the ratio of sum to be equal to x by y, Alan will have something. So the sum of Alan will look like some number k times x. Similarly, sum of Barbara will look like some number k times y, and if that is the case, then the ratio of their sums becomes equal to x over y. But we know that the sum is conserved, which is n into n plus 1 upon 2. So what we can say is we can say that k times x plus y is exactly equal to this number n into n plus 1 upon 2. Okay. So first thing is that if this k is not an integer, then obviously an answer will not exist. So if n into n plus 1 upon 2 is not divisible, So if n into n plus 1 upon 2 is not divisible by x plus y, then answer is impossible. Right, so this is the only condition when answer is impossible. Otherwise, what we do is we have to select a subset of sum equal to kx from the first n numbers. So I will describe a greedy algorithm here. I will claim that it is correct, and then I'll just prove it very simply. So what my claim here is going to be, so what I'm going to do is we will iterate. So we will iterate from n to 1 and maintain the sum that we have remaining, right? So when this sum will become 0, that means we the total sum of numbers that we have taken becomes equal to k into x. Initially this sum is going to be kx, and then we will keep decrementing this sum as and when we take a number in the subset, right? So yeah, we'll maintain the sum that we have remaining. So this is the particular value that we have to fulfill. Okay, so now let's say we are at a number I. So if we are at I, so if I is less than equal to sum, we take I, otherwise we leave I. This is the simple solution that we have, and the proof that it is working is again very simple to think about. So let's look at the first index I, where this condition will be false, where I will be greater than sum, right? So we are at a number I, we have scanned through all the values which are greater than I, right? And we know that sum is strictly smaller than I. That means that sum lies somewhere here. Okay, so sum is somewhere here, and then there is I, and then there is n. So that means we haven't even looked at sum yet. So what we can do is, now we can simply take sum, and then our sum will be equal to 0. So yeah, this is why this algorithm works. So we will keep taking values until and unless our I becomes greater than sum, and when that happens, the next number which we will take will be equal to sum itself, and that will make our sum equal to 0, right? And yeah, this is it. So this is why this solution works. Pretty simple to think about. Let's just have a look at the code. The total sum is going to be n into n plus 1 upon 2. And if the total sum is not divisible by x plus y, then obviously answer is impossible. Otherwise, answer is possible. And the sum that we want is k, is x times this value k, which is equal to total upon x plus y. And then we'll just iterate from n down to 1. And if the current number is less than equal to sum, we take the current number and decrement sum by the current number. And that is it. So yeah, this completes the solution to problem B. Let's move on to problem C now, which is a really interesting problem. So we are going to make two very important observations and then combine those two to solve this problem. Okay, so let's see what this is saying. So Ada has n ants labeled from 1 to n, and so basically there are n ants, and these n ants are currently on a stick, and we have been provided with the position of each ant on the stick, and each ant is moving either to the left or to the right with a constant speed of 1 centimeter per second. Okay, and so basically we are provided with the location of each ant on the stick as well as the direction in which that particular ant is moving, either to the left or to the right. Our task is to tell the order in which these ants will fall off the stick. Okay, so there is a stick of length equal to L centimeters, and we have been provided with the positions of each ant, and all these positions are distinct, and also the direction in which each ant is facing. So what we need to tell is, we need to tell the order in which these ants will fall off the stick. So we have to tell which ant will fall off first, which ant will fall off second, so on and so forth. Okay, so that is the problem simplified for you. So yeah, the constraints again are pretty huge here. The value L is very large, and n is also up till 10 to the 5. So yeah, in order to solve all the test sets, these are the constraints that you should look after. So let's see how we can solve this problem. Okay. Okay, so the first thing that I'm going to do is I'm going to calculate some values. Okay, so the first thing that we should do is that for each ant I, so for each ant I, what we'll do is we will ignore the presence of all other ants. So we will ignore the presence of all other ants and calculate the value out time of I, which denotes the time at which the ith ant would have fallen off the board if there were no other ants present, right? Which denotes the time at which the ith ant would have fallen off the stick had there been no other ants. Okay, so yeah, this is pretty self-explanatory. So we will calculate this value. How to calculate this value? Now this is very simple. If the ant is currently facing to the left and there is no other ant, then let's say its position is x, then it will fall out exactly at t is equals to x, right? And similarly, if an ant is facing to the right and there are no other ants present, then it will fall out at exactly t is equals to l minus x, right? So for position equals to x, so if d is equal to 0, then out time, so out time of I, so for the ith ant, what we do is if d of I is equal to 0, then out time of I is equals to p of I, okay, and otherwise out time of I is equals to L minus P of I, right? So this is a very simple to think about thing, and but like we are just calculating these values and we haven't talked about how exactly these values are going to help us. So just bear with me for now and just calculate these values, and now we'll make two observations and then we will combine those two observations to solve the problem. So let's look at the first observation. Okay. All right. Oh, okay, so we'll make a diagram and then try to make an observation. So let's say that these are the ants. Okay, these are all the ants. And let's say this is the ith ant. Okay, this is the ith ant and this is the I minus 1th ant. And let's say that the ith ant is moving to the left and this I minus 1th ant is moving to the right. Okay, something like this is happening. Okay. So what happens is that this ith ant is going to collide with the I minus 1th ant, and what will be the result of this collision? Okay, so let's try to analyze what exactly happens during a collision. Also, I didn't really explain the problem statement. So in the problem, what's happening is that ants are colliding, and as and when two ants meet, they bounce off each other and reverse their direction. So this is what is going on. Okay, and then we have to tell the order in which the ants will fall. Okay, so now let's see what happens during a collision. So if the ith and I minus 1th ants collide, what happens is that the result of this collision looks something like this. So let's say this is the ith ant, this is the I minus 1th ant, right? So before collision, this is the situation, but after the collision, so after the collision, what happens is that this ith ant is now moving to the right and this I minus 1th ant is now moving to the left. Okay, so instead of the ith ant moving to the left, the I minus 1th ant is moving to the left. Okay, so after the ith and I minus 1th ants collide, instead of the ith, the I minus 1th ant is now moving to the left. Okay, so essentially what exactly happened was that the ith ball, the ith ant imparted its motion on the I minus 1th ant. Okay, so the main observation is that the ith ant imparted its motion on the I minus 1th ant. Okay, notice that the position, so had there been no I minus 1th ant, this ith ant would continue moving to the left and the position of the ith ant would have been exactly the same as the I minus 1th ant after the collision, right? So the positions are also conserved. That is why I am saying that the entire motion of the ith ant has been completely imparted to the I minus 1th ant, right? Okay, this is I minus 1, right? Okay, so basically what happens is that the ith ant is imparting its motion to the I minus 1th ant. So now this I minus 1th ant has the motion of the ith ant and it will further collide with other ants to impart the motion of the ith ant to all those other ants, right? So the I minus 1th ant can further collide with other ants and impart the motion of the ith ant to those other ants, right? and so on and so forth, right? So this process will keep on going. So this process will keep going on until there is a final ball which will have the motion of the ith ball, and that particular ball will be the last ball which will be having the motion of the ith ball, and that ball will fall down. Okay, but the interesting thing is that that ball will fall down at t is equals to exactly out time of I. Why? Because the motion of the ith ball remains conserved. It is just that it gets transferred to different balls, but its motion remains conserved, right? So the final ball, so we don't know which ball will finally have the motion of the ith ball, which ant will finally have the motion of the ith ant. So the final ant which has the motion of the ith ant will fall off the stick at t is equals to out time of I, right? So I hope this is something that you guys can understand why exactly this final ball which will have the motion of the ith ball will fall out at this time. The reason is that the motion of ith ball remains conserved. It is just getting transferred from one ball to the other. We can see here the motion of the ith ball is getting transferred to the I minus 1th ball, and now this I minus 1th ball can transfer this motion to other balls, but the ball which will fall down will eventually fall down at t is equals to out time of I. We don't know which ball will fall down, but some ball will fall down at t is equals to out time of I. Okay, so this is the first observation that we have to make. Okay, now let's talk about the second important observation. So the second important observation is that the ants will always fall down from the endpoints. The ants will always fall down from the endpoints. What I mean by this is that let's say these are the ants which I have. So the first ball to fall down will obviously either be the leftmost ant or the rightmost ant, right? Similarly, the process of falling of ants will look something like popping elements from a DQ. We can either pop the elements from the front or we can pop the elements from the back, and that is what will happen, right? So what I mean by this is that out of all the ants which have not yet fallen, the ant which will fall down first will be either the one which has the leftmost initial position or the one which has the rightmost initial position, right? So this is another important observation, and this one is kind of intuitive to think about. Well, obviously if this is the situation of an ant, so this ant here, so this second ant can never fall before this first ant, right? Like if it's falling to the left. So if the second ant is falling to the left, it cannot fall before this first ant. And if the second ant is falling to the right, then it cannot fall before this last ant, right? So naturally, among all the ants which are remaining, the one which will fall down first will be either the one which has the leftmost initial position or the one which has the rightmost initial position. Okay, so these are the two important observations that we had to make. Now we are ready to combine these observations and come up with a solution. Okay, so what we can do is we can apply the two-pointer technique. We know that so obviously we will first sort the ants according to their initial positions, right? So now let's look at the solution. Okay, so the solution will look something like this. I have almost described the solution. It's just a matter of formalizing things now. So what we'll do is, first step is to sort the ants on the basis of initial position. Okay, this is the first thing we will do. Now what we'll do is we'll keep two pointers, one to the leftmost ant and one to the rightmost ant. So I points to the leftmost ant, not fallen yet, and J will point to the rightmost ant which is not fallen yet. Okay, and now what we have to do is we have to simply decide whether the ith ant will fall first or the jth ant will fall first. Okay, so to do that, what we'll do is, let's talk about the initial situation when I is equals to 1 and j is equals to n, right? So in this case, we know that the ant which will fall first will fall at a time which is the minimum value of out time of I for all I, right? So the first ant to fall will fall at time is equal to minimum out of all the out times, right? Why? Because at each out time of I, some ant is falling, right? So the ant which will fall first will either be the first ant or the last ant, but it will be the one which has the minimum, but it will fall at a time which is equal to the minimum value of out time I. Okay. So now what we'll do is, let k be the index of the ant which has the minimum value of out time, right? So the way we can decide whether the leftmost ant will fall or the rightmost ant will fall is simply we will look if the ant k is facing to the left or is it facing to the right. Because if an ant is facing to the left, it will only impart its motion to an ant which is to the left of it, right? Similarly, if an ant is facing to the right, it will only impart its motion to the right of it, right? So I think this is an important point which we should write in the first observation itself. So if an ant is facing left, it will impart its motion to some ball towards its left, right? And same for right, right? Okay, so now it is pretty easy to decide whether the leftmost ant will fall or the rightmost. So we will figure out the ant which has the minimum value of out time of I, and so if direction of k is equal to 0, then first ant will fall, otherwise last ant will fall. So if the first ant will fall, we can just say I plus plus, and then we can look at the ant which has the second smallest value of out time. Similarly, if the direction is equal to 1, then we can do j minus minus, and then we can look at the second smallest value of out time, and then we can keep doing this for all values of out time from smallest to largest. Okay, and this will complete our solution. The only thing we want to be careful about is that these out time values can collide. Okay, so this is a very important line. So if multiple ants fall off at the same time, then we have to output their labels in increasing order, and to do this we can just do some trivial manipulations with our code, which I'll show you, and we can handle that pretty easily. Okay, so we will just look at all the ants in decreasing order of their out times, and if the current ant is facing to the left, then the leftmost ant will fall off, otherwise the rightmost ant will fall off. Okay, so we look at all ants in increasing order of out times. So if direction of current ant is left, then leftmost ant falls off, otherwise rightmost ant falls off. Okay, so this is the solution, this is the final solution. Okay, all right. So yeah, this basically completes the solution. So these two were pretty involved observations, so I would say this is a very nice problem. So let's just have a look at the code. So the code is pretty simple. First we are taking in the ants and sorting them according to their positions. So this A vector contains all the ants sorted according to their positions. Okay, and also we are calculating out time in this vector val. So val of I is equal to L minus Pi if direction to the right, and it is equal to Pi if direction is to the left. Okay, and then we are also creating another vector in which we are storing the out time as well as the index, and then we are sorting the vector of positions and also the vector of out times. Okay, and then we iterate through the position of out times. So we iterate through the vector of out times from smallest to largest, and we look at all the values which have the same out time together, so that we can sort the results in increasing order, right? So that's the only manipulation I was talking about. So this loop is basically looking at all the values which have all the indices which have the same value of out time and putting them together. So all the indices from k to m minus 1 will be the indices which have the same value of out time. Okay, So now what we'll say is, if the direction of the current element is to the right, then we will push back the value a of j dot second, which contains the index of the rightmost ant, and otherwise we'll push the value a of I dot second into our vector, and then we will sort this vector to make sure that all the values are sorted according to their indices, and then we will put all these values into our final answer vector, which is vec. Okay, and that is it. So yeah, this is how we code it up. The code is pretty simple. The two observations were, I admit, a bit involved, but yeah, this completes the solution to problem C. Let's now move to the last problem, problem D. Okay. All right. So in this problem, there is a guy which is playing a game called Palindromic Deletions. So as a player of this game, you are given a string of length n, and then you will perform the following process exactly n times. So you will pick a random index. So you will pick an index uniformly at random from the string, and then you will delete the character at that position, and then you will end up with a new string with one fewer character, obviously. So now if the new string is a palindrome, then you basically eat a piece of candy in celebration. So that is the game. So you do this process exactly n times, and the question that you have to answer is, given a starting string, what is the expected number of candies that you will eat during the game? Okay. So if you don't know about probability and expected value, I don't think you should move ahead with solving this problem. You should first learn about these concepts and solve some simple problems from code forces maybe. But if you know about it, then we can go ahead and solve this problem. I don't think this is very difficult. Okay. So yeah, you have to tell the expected number of candies that you will eat during the entire game. We can look at the constraints here. To solve test set 2, the value of n, which is the length of the string, is up to 400. Okay, and this means we can do a solution which is around O of n cube, right? So yeah, keeping that in mind, let's see how we can solve this problem. Okay. So as I said before, this problem is not really that difficult. So we just have to make one observation, and then we can solve this problem. Okay. So what we'll do is, we will look at all palindromic subsequences, and try to find out their contribution to the expected value. And by linearity of expectation, we can say that the total expected value, which will be equal to the sum of the contribution of each palindromic subsequence. Okay. If you don't know about linearity of expectation, again, I think you should first learn about it. So by linearity of expectation, the final answer will be equal to the sum of contribution of each palindromic subsequence. Sorry. So why am I looking at palindromic subsequence? The reason is that when I am removing some candies, what I will be left with is a subsequence, right? So even before this, I should write, so when we remove some candies, when we remove some characters, we are left with a subsequence of the initial string, and if it is palindromic, then we eat a candy, right? So if it is palindrome, we eat a candy, right? So yeah, so basically we have if we have a palindromic subsequence, what we have to calculate is, we have to calculate its contribution to the expected value, right? So let's say we have a palindromic subsequence x. So we have a palindromic subsequence x. Okay, so we have a palindromic subsequence x. Let c of x be its contribution. Obviously, we cannot iterate over all these palindromic subsequences, because there can be a lot of palindromic subsequences in a string, right? The number of subsequences is 2 raised to the power n, and in the worst case, all of them can be palindromic. So we can do that in the first test set, but we can't do that for the second test set, right? So we have to calculate. So we have to think about something, and we have to reduce the time complexity, and that will come if we find out an expression c of x, which will be the contribution of each substring. So let's try to find this out. To expected value. So now let's try to write an expression for c of x. So the expression of c of x is nothing but the probability that we get this substring during the probability that we get this subsequence during the game multiplied by 1. So let me write it down. Probability that we get this subsequence. So probability that we get x during the game multiplied by 1. So it's multiplied by 1 because for each time we get this subsequence x, we will eat exactly 1 candy. So its contribution will be exactly 1, and that has to be multiplied with the probability that we get x, right? So this is how probability and expected value works, right? So now we just have to figure out an expression for the probability that we get x during the game. So let's say that the length of x, so length of x is equal to k. Okay, so out of all the n characters, these k characters correspond to the string x, right? So these k arbitrary characters, they can be at any position, but we will find the expression for probability of getting x during the game, and what we will realize is we will realize that this c of x will only depend on k, and the reason being, so let's try to calculate this probability. Let's say this probability is equal to p. Okay, so now we will find out p. So for p, what we have to do is, so we have to, probability is basically the number of favorable ways divided by the total number of ways, right? So number of favorable ways. So for number of favorable ways, what we are basically doing is, so when we are left with a string of with a subsequence of length k, that means we have removed n minus k characters already, right? And among all these k characters which belong to this subsequence, I haven't removed any character, right? So basically I will, so in a favorable way, I will remove all remaining n minus k characters in an arbitrary fashion, right? And the number of ways to do that is nothing but n minus k factorial, right? So in the first n minus k turns, if I just randomly remove values in any order from the remaining n minus k characters, then I will be left with this subsequence, right? So these are all the favorable ways. And now let's calculate the total number of ways. So we are removing n minus k characters. So for the first character, we have n choice. Similarly, for the second character, we have n minus 1 choice. For the third character, we have n minus 2 choice. And for the last character, we will have x plus 1 choices, right? So yeah, these are the number of these are the total number of ways, and this expression is basically nothing but n factorial divided by x factorial, right? You can clearly see here this expression is nothing but n factorial divided by x factorial, and so the probability is nothing but the number of favorable ways divided by the total number of ways. So probability becomes n minus k factorial divided by this n factorial upon x factorial, which simplifies to nothing, so n factorial upon k factorial, sorry, so this should be k. So this is nothing but k factorial into n minus k factorial divided by n factorial. So this is the expression of the probability that we get a particular palindromic subsequence x of length equal to k. So what we realize here is that p is only dependent on k, which is the length of the subsequence, right? That means we don't have to go over each subsequence separately. If somehow we can calculate the total number of palindromic subsequences for all k from 0 to n minus 1, and then it becomes really easy because we can calculate this value. So we will calculate this value and just multiply it with the total number of subsequences of palindromic subsequences of length k and sum up over all k, and that will be our answer, right? Because we can take all the palindromic subsequences of a particular length together, because their contribution to the expected value will be equal and will be equal to this, right? So what we can do is, for each k, we find the total number of palindromic subsequences of length equals to k, and multiply it. So this expression is P of k, right? This is the contribution to the expected value of any palindromic subsequence of length k, and multiply it with P of k and add it to our answer. So for each k from 0 to n minus 1. So we will do this for each k from 0 to n minus 1 and we will get our answer, right? So this is 50% of the problem done. Now the only question is, how do we calculate these values, which is the total number of substrings, total number of palindromic subsequences of length k, right? So now how do we calculate these values? Well, we can basically apply dynamic programming, right? So how to calculate number of palindromic subsequences of length k. So basically we will use dynamic programming to solve this problem, and the states of our DP will look something like this. So DP ijk is equals to number of palindromic subsequences of length k which lie in S of I to j, right? That means that particular subsequence is a subsequence of this substring from I to j, right? So in starting from I and ending at j, so how many palindromic subsequences of this particular substring exists whose length is equal to k? So for each k, the values which we are interested in is nothing but dp1 and k, right? So because S of 1 to n is the entire string, and we are interested in the number of palindromic substrings of length k in the entire string. So these are the values in which we are interested, right? Now how to make transitions? I will just briefly describe the transitions and then I will show you the code, which will make things much clearer. So the first thing is that dp ijk will be equal to dp I plus 1 jk plus dp I j minus 1 k minus dp I plus 1 j minus 1 k. And now why is this so? So let me try to explain. Let's say this is I and this is j, this is I plus 1, this is j minus 1, right? Okay, so what happens is that first I am taking dp I plus 1 jk, which means all the palindromic substrings which can be formed from this all the palindromic subsequences which can be formed from here, and then I am taking dp I j minus 1. So all the palindromic subsequences that can be formed from here. But what we realize is we are taking this particular region twice, right? Which is from I plus 1 to j minus 1. So that is why we have to subtract dp I plus 1, j minus 1 and k. Okay. So I hope it's clear enough. Now the only thing which we have missed is what if our subsequence contains both I and j, right? So that can only happen if S of I is equal to S of j. So if S of I is equal to S of j, then basically what happens is that two characters will be taken already. So that is the ith character and the jth character, and then we'll be left with k minus 2 characters. So what we can do is we will write dp I j k plus equal to dp I plus 1 j minus 1 and k minus 2, because for any palindromic subsequence of length k minus 2 which belongs to this middle region from I plus 1 to j minus 1, we can add S of I and S of j to its front and end respectively, and we will again get a palindromic subsequence whose length will be exactly equal to k, right? So these are the transitions which I have described briefly. Once we have all these dp values calculated, we can simply do this for all k. We will multiply dp1 and k with p of k, right? So for all k from 0 to n minus 1, add p of k into dp of 1 and k to answer, right? So this is it. Finally we will have the correct answer. So I hope this was not very overwhelming, and I tried to explain it in the easiest way that I could, right? So this is the entire solution. Let's just have a look at the code for better understanding. Okay, so I initialize my DP with all zeros. So one important thing to note here is that you cannot take long as your DP array. You have to take your DP array as an array of integers, right? And this is one important thing to note here, because of some memory issues and stuff like that. So that is why I lost one penalty attempt. Anyways, so you initialize all your DP values with 0, and then you iterate for I, j, and then you iterate for k, and basically you say that dp I j 0 will obviously be 1, because it will be the empty subsequence, and dpij1 will always be equal to j minus I plus 1. And then you can iterate from 2 to n, and then you can apply the transitions as I have discussed before, and this is it. So then you can simply iterate from 0 to n minus 1, and you can calculate these p values on the go. This is really easy: n minus k factorial multiplied by k factorial divided by n factorial, and then you can multiply these values with dp1 and k and add that to your answer, and that will give you the final answer, right? So this completes the solution to the last problem, and that is all that I had planned for today. So thank you so much for watching, and I will see you in the next one.